In this video, we are going to explore, is this whole universe a quantum thing? If you share a passion for space and physics, you're in the right place. This channel is dedicated to curious minds who love exploring the deeper workings of the cosmos. Let me know in the comments whether you're a student or a general science enthusiast. Imagine you are holding a coffee cup right now. Go ahead, picture it in your hand. You can feel its weight, its temperature, the smooth ceramic surface against your skin. This cup seems absolutely real, absolutely solid, absolutely there. But what if I told you that everything you think you know about this simple coffee cup is wrong? What if the cup is not really solid at all? What if, when we look close enough, the cup and everything else in the universe stops making sense in the way we expect it to? For hundreds of years, scientists thought they understood how reality worked. They could predict where planets would be decades in advance. They could calculate how fast a cannonball would fly. The universe ran like a perfect machine, and we had the instruction manual. But then, about 100 years ago, scientists started looking really close at things. They peered into the world of atoms and particles, expecting to find tiny little balls bouncing around like microscopic billiard balls. Instead, they found something so weird, so bizarre, so absolutely impossible by the rules of everyday life, that it shattered everything we thought we knew. What they found was the quantum world. And here is the thing that should keep you watching for the next 2.5 hours. That quantum weirdness might not be limited to tiny particles. It might be everything. The coffee cup, your hand holding it, your brain thinking about it, the planet beneath your feet, the stars in the sky, and the very fabric of space and time itself might all be quantum things. By the end of this journey, you will never look at reality the same way again. That coffee cup will become one of the most mysterious objects in the universe. So let me ask you the question that has haunted physicists for a century. Is this whole universe a quantum thing? Let us find out together. Chapter 1. The world we think we know. Before we can understand how reality broke, we need to understand what people thought reality was. Picture yourself back in the year 1800. If you were a physicist back then, you lived in a beautiful, orderly universe. Isaac Newton had given humanity an incredible gift, a set of rules that could predict almost everything. Drop an apple, and Newton could tell you exactly how fast it would fall and precisely where it would land. Fire a cannonball, and you could calculate its arc through the air with perfect accuracy. Look up at the planets, and you could predict where Jupiter would be not just tomorrow, not just next year, but centuries into the future. This was not guesswork. This was certainty. The universe operated like the most perfect clock ever built. Every gear meshed with every other gear. Every planet followed its orbit with mathematical precision. If you knew where something was and how fast it was moving, you could predict its entire future. You could also work backward and figure out its entire past. Time flowed in one smooth direction, like a river. Space was just an empty stage, where things happened. Matter was made of tiny, hard particles that bumped into each other, following simple rules. Think about billiard balls on a pool table. You hit the white ball with your cue. It rolls across the green felt and strikes the red ball at a particular angle with a particular speed. If you know all those details, you can calculate exactly where both balls will go. The red ball cannot decide to suddenly swerve left because it feels like it. The white ball cannot be in two places at once. Everything is determined, everything is predictable, everything makes sense. This classical physics matched our everyday experience perfectly. When you throw a baseball, it does not disappear and reappear somewhere else. When you look at your car keys, they do not suddenly become uncertain about whether they exist. The world we experience follows rules that make intuitive sense to our brains. And for 200 years, scientists could describe this world with mathematics that was so accurate, so reliable, so beautiful, that many physicists in the late 1800s actually thought they were done. They believed that physics was essentially complete. Sure, there were a few tiny loose ends to tie up, a few small questions to answer, but the big picture was finished. Oh, how wrong they were! Those tiny loose ends were about to unravel the entire fabric of reality. The universe was about to show scientists that everything they thought they knew was just an approximation, just the surface of something far stranger and far more wonderful than anyone had imagined. The perfect clockwork universe was about to reveal itself as something much more mysterious. Chapter 2. The Cracks Appear. The year is 1900. Physics is riding high. Scientists gather at conferences confident that they understand the universe. But there is this one annoying little problem that nobody can solve. It is called the ultraviolet catastrophe, and it involves something as simple as hot metal glowing. When you heat up a piece of metal, it glows red, then orange, then yellow, then white as it gets hotter. This seems simple enough, but when physicists tried to calculate how much light should come off at different colors using their beautiful classical equations, the math told them something insane. According to classical physics, a hot object should release infinite energy in ultraviolet light. Obviously, hot objects do not release infinite energy, because if they did, the universe would have exploded a long time ago. Enter Max Planck, a German physicist who was desperate to solve this problem. Planck tried everything using classical physics. Nothing worked. Finally, in an act of what he later called desperation, he tried something radical. He proposed that energy does not flow smoothly like water. Instead, energy comes in discrete chunks, like coins. You can have 1 coin or 2 coins, but you cannot have 1.5 coins. Planck called these chunks quanta, from the Latin word for amount or quantity. When he used this chunky energy in his equations, suddenly everything worked. The ultraviolet catastrophe disappeared. The math matched what actually happens with glowing metal, but here is the thing. Planck thought this was just a math trick. He did not believe energy really came in chunks. He thought he had just found a clever mathematical shortcut and that eventually someone would figure out how to do it properly using smooth, continuous energy. Planck spent years trying to get rid of his own quantum idea. he could not. The universe seemed to genuinely work this way, but it made no sense. How could energy be chunky? Energy flowing is like water flowing from a faucet, smooth and continuous, right? Then along came Albert Einstein in 1905. This was Einstein's miracle year, when he published multiple papers that changed physics forever. One of those papers was about something called the photoelectric effect. Scientists had noticed that when you shine light on certain metals, electrons pop out. But weirdly, if you use dim blue light, electrons come flying out with lots of energy. If you use bright red light, nothing happens at all. Classical physics said this was impossible. Light is a wave, and brighter light should mean more energy regardless of color. But that is not what happened. Einstein took Planck's quantum idea seriously. He proposed that light itself comes in particles, little packets of energy that we now call photons. Each photon has an amount of energy determined by its color. Blue photons have more energy than red photons. When a blue photon hits an electron, it has enough energy to knock the electron loose, like a cue ball hitting a billiard ball. A red photon does not have enough energy, so even if you have 1,000,000 red photons hitting the metal, none of them can knock an electron loose individually. It is like trying to break down a door by throwing ping-pong balls at it. Throw 1,000,000 ping-pong balls and the door stays shut. Throw one bowling ball and the door crashes open. Einstein got the Nobel Prize for this discovery. Not for relativity, which is what he is famous for, but for proving that light comes in quantum chunks. This was the moment when quantum stopped being just weird math and became real. Light, which everyone knew was a wave because we could see it creating interference patterns and diffracting around corners, was also somehow made of particles. This made no sense whatsoever. How can something be both a wave and a particle? This is like saying something is both wet and dry at the same time, or both here and there simultaneously. The cracks in classical physics were now becoming chasms. Scientists had opened a door expecting to find a small closet, and instead they found themselves staring into an abyss of weirdness that seemed to have no bottom. And the strangest discovery was still to come. The one that would make even Einstein uncomfortable. The one that would show that reality itself changes when you look at it. Chapter 3. The Double-Slit Nightmare. If you want to understand why the quantum world is so disturbing, so counterintuitive, so absolutely mind-breaking, you need to understand one experiment. It is called the double-slit experiment, and it has been called the most beautiful experiment in physics. It is also the most disturbing. This single experiment contains all the weirdness of quantum mechanics in one neat package. And the best part? You can understand it without any math. You just need to follow along carefully, because what happens in this experiment should be impossible. Let me set the stage. Imagine you have a wall with 2 narrow slits cut into it. Behind that wall, you have a screen that records where things hit it. Now, let us start simple. Take a machine gun and fire bullets randomly at the wall. Some bullets go through the left slit, some go through the right slit. Some hit the wall and do not go through at all. The bullets that make it through hit the screen behind the wall. What pattern do you see? You see two bright strips on the screen, one behind each slit. This makes perfect sense. Bullets are particles. They go through one slit or the other. You get two bands on the screen. Simple. Now let us try waves. Fill a tank with water and make waves heading toward a barrier with two slits. The waves pass through both slits and spread out on the other side. But here is where waves do something particles cannot do. The waves from the left slit and the waves from the right slit meet on the other side. Where two wave peaks meet, you get a bigger wave. Where a peak meets a trough, they cancel out. This creates what is called an interference pattern. Instead of two bands, you get multiple bands alternating between high waves and calm water. This is the signature of waves. Only waves create interference patterns. Particles cannot do this because a particle goes through one slit or the other, never both. Now comes the quantum nightmare. Let us shoot electrons at the two slits. Electrons are particles, right? They are little chunks of matter with mass and charge. So they should behave like bullets and create two bands on the screen. But they do not. Electrons create an interference pattern. Multiple bands, just like waves. The electrons are somehow going through both slits at the same time and interfering with themselves. But wait, you say, maybe electrons are just waves, not particles. Let us check. Here is where it gets really weird. Let us shoot the electrons one at a time. We fire a single electron at the slits, wait for it to hit the screen, and then fire another one. Each electron hits the screen at one spot, like a particle. But as we fire more and more electrons one by one, the interference pattern slowly builds up. Each individual electron is definitely a particle, hitting one specific spot. But collectively, they are behaving like waves, creating an interference pattern. Each electron is somehow going through both slits simultaneously and interfering with itself. Your brain is probably hurting right now, and it should be. But it gets worse. Let us put detectors at the slits to see which slit each electron actually goes through. We want to catch the electron in the act of going through both slits. We turn on the detectors and start firing electrons. And the moment we do this, the interference pattern disappears. Now we get two bands, just like bullets. The electrons start behaving like normal particles that go through one slit or the other. The act of watching, of measuring which slit the electron goes through, changes what the electron does. Scientists tried everything to get around this. Maybe the detector disturbs the electron physically. They built gentler and gentler detectors. Pattern still disappeared. Maybe the detector adds energy? They built detectors that added essentially zero energy. Pattern still disappeared. Maybe it is something about consciousness? They had unconscious automatic detectors record which slit without anyone looking at the results until later. Pattern still disappeared even though nobody knew which slit each electron went through until after the experiment was done. It was not about human consciousness. It was about measurement itself. The universe seems to have a rule. When you are not looking, quantum particles exist in multiple states simultaneously. They go through both slits at once. They interfere with themselves. They are in what physicists call a superposition of possibilities. But the moment you measure which possibility is actually real, the superposition collapses. The particle picks one option and sticks with it. The universe goes from fuzzy possibility to definite reality right before your eyes. This is not a measurement problem in the sense that our instruments are not good enough. This is reality itself behaving differently when measured versus when not measured. It is as if the universe has not decided what the electron is doing until forced to by measurement. And this raises a question so deep, so philosophical, so disturbing that physicists are still arguing about it 100 years later. What is real when we are not looking? Does the moon exist when nobody is observing it? Einstein asked this question, and he believed the answer was obviously yes. But quantum mechanics seems to suggest something far stranger. It suggests that the universe is not a collection of definite things with definite properties. It is a collection of possibilities that become real only when measured. This is where classical physics died. You cannot explain the double-slit experiment with billiard ball particles following definite paths. You cannot explain it with smooth, continuous waves either. You need something new, something that nobody had ever imagined before. You need quantum mechanics. And once scientists started unpacking what quantum mechanics really means, they discovered rules so bizarre that even the people who discovered them could not believe what they were seeing. Chapter 4. Superposition, being two places at once. Let us talk about what might be the single weirdest rule in all of quantum mechanics. It is called superposition, and it means that quantum particles can exist in multiple states at the same time. Not that we do not know which state they are in. Not that they are rapidly switching between states. They are actually in multiple states simultaneously. The particle has not decided yet. And this is not some philosophical interpretation. This is what the math says, and more importantly, this is what experiments confirm over and over again. Think back to the double-slit experiment. The electron goes through both slits at once. It is not that we do not know which slit it went through. It is that the question does not even have an answer until we measure. The electron is in a superposition of going through the left slit and going through the right slit. Both possibilities exist together in a weird quantum mixture. Only when we measure does the electron pick one path or the other. Before measurement, asking which slit the electron went through is like asking what color happiness is. The question does not apply. The electron is not secretly going through one slit while we are ignorant about which one. It is genuinely going through both. Now you have probably heard of Schrödinger's cat. This is the thought experiment that everyone brings up when talking about quantum mechanics, usually incorrectly. Let me explain what it actually means. Erwin Schrödinger, one of the founders of quantum mechanics, wanted to show how absurd quantum rules would be if they applied to big everyday objects. He imagined putting a cat in a box with a quantum device that has a 50% chance of releasing poison. According to quantum mechanics, until you open the box and measure what happened, the quantum device is in a superposition of both having released the poison and not having released it. And if that is true, then the cat must be in a superposition of being both alive and dead simultaneously. Now, most people misunderstand this. They think Schrödinger was saying the cat is both alive and dead. Actually, Schrödinger was saying this proves quantum mechanics must be incomplete. He was saying, look how ridiculous this is. Obviously, cats are not both alive and dead, so quantum mechanics must be missing something. But here is the shocking twist. As far as we can tell, Schrödinger was wrong. Quantum mechanics really does say the cat is in superposition. The reason we never see alive and dead cats is not because quantum mechanics breaks down at large scales. It is because of something called decoherence, which we will get to later. But the principle holds. Superposition is real. Let me give you a way to think about this that might help. Imagine a coin that you are about to flip. Classical physics says the coin is currently showing heads, and when you flip it, it will follow a definite path through the air and land on either heads or tails. At every moment, the coin is in one state. Quantum mechanics says something radically different. It says that before you flip the coin and look at the result, the coin is in a superposition of heads and tails simultaneously. Not that it is one or the other, and we do not know which. It is both. The coin exists in a state that has no equivalent in everyday experience. It is not oscillating between heads and tails. It is not randomly one or the other. It is in a state where the question of whether it is heads or tails does not have an answer yet. This raises the most disturbing question. What does measurement do? When you look at the coin, the superposition collapses. The coin becomes definitely heads or definitely tails. But what counts as a measurement? Does it require a conscious observer? Does the coin collapse when a camera looks at it? What about a bacterium? What about an atom? This is called the measurement problem, and it is one of the biggest unsolved puzzles in physics. We know measurement causes collapse. We can measure when it happens. But we do not know why it happens, or what exactly counts as a measurement. Some physicists think consciousness causes collapse. Most think this is wrong. Some think the wave function never collapses at all, and instead the universe splits into multiple versions every time a measurement happens. We will get to that wild idea later. But for now, the key point is this. Superposition is not a metaphor. It is not a lack of knowledge. It is reality itself being in multiple states at once. And experiments have confirmed this thousands of times in thousands of different ways. Particles really do exist in superposition. They really are in multiple places or multiple states simultaneously. And this is not limited to particles we cannot see. Scientists have put increasingly large objects into superposition. Molecules with hundreds of atoms, tiny mirrors. Eventually, we might put something big enough to see with the naked eye into superposition. At what point does superposition stop? As far as we can tell, it never stops. It just becomes harder and harder to observe as things get bigger. Which raises an incredible possibility. Maybe everything is in superposition all the time, and we just cannot see it because we are too big and too connected to the environment. Maybe the whole universe is a quantum superposition. But before we get there, we need to understand another quantum rule that Einstein called spooky. Chapter 5. Entanglement, spooky connection. If superposition broke your brain, get ready for entanglement to put it back together upside down. Entanglement is so weird that Albert Einstein refused to accept it. He wrote papers trying to prove it was impossible. He called it spooky action at a distance and insisted it showed quantum mechanics was incomplete. But Einstein was wrong. Entanglement is real, and it might be the single strangest phenomenon in the entire universe. Here is how entanglement works. Take two particles and make them interact in a certain way. Maybe they are created together, or maybe they collide. These particles can become entangled. This means their quantum states become linked in a way that has no equivalent in classical physics. Once entangled, measuring one particle instantly affects the other particle, no matter how far apart they are. And when I say instantly, I mean instantly. Not speed of light, instant. Measure one particle on Earth, and its entangled partner on the other side of the galaxy reacts at that exact same moment. Let me give you an example that makes this clear. Imagine you have two coins that are entangled. You put one coin in a box on Earth and send the other coin to Mars. The coins are in a superposition where their combined state is both heads plus both tails, but never one heads and one tails. Now you open the box on Earth and look at your coin. Let us say it shows heads. At that instant, before any signal could possibly travel to Mars, the coin on Mars becomes tails. Not that it was already tails and you just found out. It becomes tails at the moment you measure yours as heads. The measurement on Earth changes the reality on Mars faster than light. Now, before you ask, no, you cannot use this to send messages faster than light. The key is that when you measure your coin, you get a random result. You cannot control whether you get heads or tails. So you cannot encode a message. The person on Mars also gets a random result when they measure their coin. Only later, when you compare your results, do you discover that your results were always opposite. So no information travels faster than light, but the correlation between the particles is established instantly. The universe somehow keeps track of entangled particles across any distance and ensures they remain correlated. Einstein hated this because he believed in locality. Locality means that things are only directly affected by their immediate surroundings. If you want to affect something far away, you have to send a signal, and that signal cannot travel faster than light. Entanglement seems to violate locality. The measurement on Earth seems to directly affect the particle on Mars without any signal traveling between them. Einstein, along with Boris Podolsky and Nathan Rosen, wrote a famous paper in 1935 arguing that quantum mechanics must be incomplete. There must be hidden variables, secret information that we cannot see, that determines what each particle will do when measured. The particles must be carrying instructions from when they were created, like secret notes in their pockets. That way, they would not need to communicate faster than light. They would just be following their pre-programmed instructions. This became known as the EPR paradox, named after Einstein, Podolsky and Rosen. For 30 years, this was just philosophy. No one knew how to test whether Einstein was right. Then, in 1964, a physicist named John Bell figured out a way to test it. Bell came up with a mathematical inequality that must be true if Einstein's hidden variables exist. But if quantum mechanics is right and there are no hidden variables, then experiments should violate Bell's inequality. This was enormous. This meant you could actually test whether Einstein or quantum mechanics was right about the nature of reality. Starting in the 1970s and continuing to this day, scientists have performed Bell test experiments thousands of times with increasingly sophisticated setups. And the results are absolutely clear. Bell's inequality is violated. Quantum mechanics wins. Einstein was wrong. There are no hidden variables. Entanglement is real. The particles genuinely do not have determined properties until measured, and the measurement of one really does instantly affect the other. In 2022, the Nobel Prize in Physics was awarded to 3 scientists for their experiments proving entanglement is real, and for developing quantum technologies based on entanglement. This is not fringe physics. This is not controversial. Entanglement is now an accepted, proven fact about our universe. And it means something profound. The universe is not made of separate, independent objects. At a fundamental level, quantum systems are connected in ways that transcend space. Once 2 particles become entangled, they form a single quantum system, even if they are separated by billions of light years. You cannot describe one without describing the other. They are, in a deep sense, not really separate anymore. Now, think about what this means for the universe as a whole. After the Big Bang, everything in the universe was squeezed into an incredibly tiny space. Everything was interacting with everything else. This means that in principle, everything in the universe could be entangled with everything else. Every particle in your body might be entangled with particles on the other side of the universe. The universe might be one giant web of entanglement connecting every single thing. We cannot usually see this cosmic entanglement because it gets washed out by interactions with the environment, a process we will discuss later. But at a fundamental level, the universe might not be a collection of separate objects at all. It might be one unified, entangled quantum system. And if the universe is one big entangled system, then in a very real sense, the universe is a quantum thing. But we are getting ahead of ourselves. We still need to understand another quantum rule that makes even superposition and entanglement seem almost reasonable by comparison. We need to talk about uncertainty and how nature has a fundamental fuzziness built into the very fabric of reality. Chapter 6. Uncertainty, nature's blur. There's a word in quantum mechanics that everyone has heard, but almost nobody understands correctly. That word is uncertainty. When Werner Heisenberg discovered his uncertainty principle in 1927, he revealed something so fundamental about reality that it still makes physicists uncomfortable today. And the discomfort comes from a simple fact. Heisenberg's uncertainty principle is not about our inability to measure things accurately. It is about reality itself being fundamentally uncertain. Let me explain what this means. In classical physics, every particle has a definite position and a definite velocity at every moment. Maybe you do not know where the particle is or how fast it is moving, but the particle knows. The information exists out there in the universe. If you had perfect instruments, you could measure position and velocity to arbitrary precision. Classical physics says there is no limit to how accurately you can know everything about a particle. Quantum mechanics says no. There is a limit, and it is not a limit of our technology. It is a limit of reality. According to Heisenberg's uncertainty principle, the more precisely you know where a particle is, the less precisely you can know how fast it is moving. And this is not because measuring position disturbs the velocity. It is because the particle does not have both a definite position and a definite velocity simultaneously. If a particle has a very definite position, its velocity is fundamentally uncertain, spread out over a range of possibilities. If a particle has a very definite velocity, its position is fundamentally uncertain, smeared out over space. Think about this carefully, because it is weird. Imagine you have an electron, and you measure its position very precisely. You pin it down to a tiny region of space. At that moment, the electron's velocity becomes uncertain. Not uncertain to you. Uncertain, period. The electron does not have a definite velocity. If you then measure its velocity, you will get some value, but that value was not predetermined. The electron had a range of possible velocities, existing in superposition of all those velocities simultaneously. The measurement forces it to pick one. But now, because you measured velocity precisely, the position has become uncertain again. You cannot win. You cannot have both simultaneously. This is not about the observer disturbing the system. This is about the universe itself having a fundamental graininess or fuzziness at small scales. There is a minimum amount of uncertainty built into reality. You can trade position uncertainty for velocity uncertainty or vice versa. But you can never get rid of the uncertainty entirely. This is written into the laws of nature at the deepest level. Heisenberg's uncertainty principle comes directly from the wave nature of matter. Remember, quantum particles are also waves. A wave that is very localized, concentrated in one small region, must be made up of many different wavelengths mixed together. Those different wavelengths correspond to different velocities. So, a particle with a definite position is automatically a mixture of many velocities. Conversely, a wave with a definite wavelength, and thus a definite velocity, must be spread out over space. It cannot be localized to one position. This is not a bug in quantum mechanics. This is a direct consequence of particles being waves and waves being particles simultaneously. And uncertainty applies to more than just position and velocity. It applies to energy and time as well. The more precisely you know the energy of a system, the more uncertain you are about when that energy was measured. This has a bizarre consequence. Particles can briefly borrow energy from the universe as long as they pay it back quickly enough that nobody notices. This leads to virtual particles popping in and out of existence everywhere, all the time. Even empty space is not truly empty. It is seething with quantum fluctuations, pairs of particles appearing and disappearing in the time allowed by the uncertainty principle. Here is why this matters for our big question about whether the universe is quantum. Uncertainty is unavoidable in quantum mechanics. If something obeys the uncertainty principle, it is definitely quantum. And guess what? Everything we have ever measured obeys the uncertainty principle. Electrons, photons, atoms, molecules, nothing escapes it. We have even tested uncertainty with molecules containing hundreds of atoms. They still obey Heisenberg's principle. There is no size at which uncertainty stops applying. As far as we can tell, uncertainty is universal. This means that at some level, nothing in the universe can be perfectly still or perfectly located. Everything is jiggling, fluctuating, uncertain at a fundamental level. Even the atoms in your body right now are not sitting in definite positions. They are existing as smeared-out probability clouds, waves of possibility that we perceive as definite objects only because we are so much bigger than atoms. The universe is restless at its core. Reality is blurry when you look close enough. And this blurriness never goes away. It is not a feature of our ignorance. It is a feature of existence. Think about what this means. Your position right now is not perfectly definite. You are slightly uncertain about your own location. Not by much, because you are big and massive, but there is uncertainty there. Every particle in your body has uncertain position and uncertain velocity. You are made of quantum fuzziness. And if you are made of quantum fuzziness, then you are made of quantum mechanics. You are a quantum thing. But we still have not addressed the elephant in the room. All these quantum rules, superposition and entanglement and uncertainty, are described by something called the wave function. This mathematical object contains all possible information about a quantum system. It tells you the probability of finding a particle in any location with any velocity. It describes the superposition of all possible states. It is the recipe for quantum reality. But what is the wave function? Is it just math? Just a tool for making predictions? Or is it something real? And if it is real, what happens when it collapses? Let us dig into this mystery because it is going to lead us to some of the strangest ideas in all of science. Chapter 7. Wave Function, Reality's Recipe. Imagine you want to describe everything you could possibly know about an electron. Where it is, how fast it is moving, what direction it is spinning, all of its properties. In classical physics, you would just list numbers. Position x, velocity y, spin up. Done. The electron has definite values for everything. But in quantum mechanics, you cannot do that. The electron does not have definite values for all its properties simultaneously. Instead, you describe the electron with something called a wave function. The wave function is a mathematical object that contains all the information about a quantum system. But it does not tell you where the particle is. It tells you where the particle might be. The wave function is a map of possibilities. At every point in space, the wave function has a value, and that value tells you the probability of finding the particle there if you measure. Where the wave function is large, the particle is likely to be found. Where the wave function is small, the particle is unlikely. Where the wave function is zero, the particle definitely will not be found. This is already strange. The wave function does not describe what is. It describes what could be. But it gets stranger. Remember superposition? The wave function is what allows superposition to happen. The electron going through both slits is described by a wave function that has two peaks, one at each slit. The electron is not secretly at one slit or the other. The wave function is the electron, and the wave function exists at both slits simultaneously. The wave function is not a description of our ignorance about where the electron really is. The wave function is the reality of the electron. At least that is one interpretation, and it is the interpretation most physicists use in practice. The wave function is not just a mathematical tool. It is the most complete description of reality we have. When nothing is measuring the electron is its wave function, spread out in space as a cloud of possibility. Then, when you measure the electron's position, something dramatic happens. The wave function collapses. Instantly, the spread-out cloud of possibility snaps to one point. The electron appears at one location. All the other possibilities disappear. This collapse is one of the deepest mysteries in physics. The wave function evolves smoothly and predictably according to the Schrödinger equation. Scientists can calculate exactly how the wave function will change over time, but the moment a measurement happens, the smooth evolution stops and collapse occurs. The wave function goes from spread out to localized instantly. This seems to violate everything else we know about physics. Nothing else in physics involves instantaneous change. Everything else flows continuously. But wave function collapse is a discontinuous jump. What causes collapse? Nobody knows. The Schrödinger equation does not include collapse. Collapse has to be added as a separate rule. This is weird. It is like discovering that cars obey the laws of aerodynamics and friction most of the time, but occasionally they teleport for no reason. The wave function follows beautiful mathematical rules until it suddenly does not. Why? What counts as a measurement? Where is the line between the quantum world that obeys superposition and the classical world that does not? Some physicists have proposed that collapse is real, that something physical happens during measurement that makes the wave function suddenly localize. Others have proposed that collapse is not real at all, that the wave function never collapses, and that what we perceive as collapse is actually the universe splitting into multiple branches. We will explore that mind-bending idea later. Still, others think the wave function is not a real physical thing at all, but just a tool for calculating probabilities and asking what collapses is like, asking what happens when your calculator runs out of battery. But here is what we know for certain. The wave function works, It predicts the results of every quantum experiment ever performed with astonishing accuracy. Quantum mechanics is the most accurately tested theory in the history of science. Some quantum predictions have been verified to 10 decimal places. The wave function might be weird, it might be mysterious, it might make philosophers uncomfortable, but it is not wrong. It describes reality more accurately than any other theory humans have ever devised. And the wave function is not limited to single particles. You can have wave functions for 2 particles, and those wave functions can describe entanglement. You can have wave functions for molecules, for atoms in a crystal, for electrons in a superconductor. In principle, you can have a wave function for any system, no matter how big. There is even, in principle, a wave function for the entire universe. This is a stunning idea. The whole universe, every particle, every atom, every star, every galaxy, could be described by one giant wave function. This universal wave function would contain every possibility for every particle everywhere. It would describe the superposition of all possible configurations of all matter and energy in the cosmos. This is not science fiction. This is a logical extension of quantum mechanics. If quantum mechanics applies to one particle, and it applies to 2 particles, and it applies to molecules and atoms and bigger systems, then why would it suddenly stop applying? Where is the cutoff? As far as we can tell, there is no cutoff. The wave function can describe systems of any size. And if the universe has a wave function, then the universe is quantum. It is not that the universe contains some quantum things and some classical things. Everything would be quantum. Classical behavior would be an approximation that emerges when systems become large and interact with their environment. But at the fundamental level, the universe would be one giant quantum system in superposition of all possible states. This raises the ultimate question: does the wave function of the universe ever collapse? Or does it just keep evolving in superposition forever? Is there some cosmic measurement that collapses the universe's wave function? Or are we, as conscious observers, the ones who collapse it whenever we measure something? Or, in the most radical interpretation, does the universe never collapse at all, and instead it branches into parallel universes every time a quantum event occurs? Before we can answer these ultimate questions, we need to understand why we do not see quantum weirdness in everyday life. Why are cats either alive or dead, but never both? Why does your car have a definite position instead of being smeared out across the parking lot? The answer lies in a phenomenon called decoherence, and understanding it will finally allow us to scale up quantum mechanics from particles to people, to planets, to the entire universe. Chapter 8. The Measurement Problem. We have been dancing around it, but now we need to face it head-on. Quantum mechanics has a problem at its heart, a question so fundamental that physicists have been arguing about it for nearly 100 years without reaching consensus. It is called the measurement problem, and it goes like this. Quantum mechanics gives us 2 completely different rules for how systems evolve. When you are not measuring a quantum system, it evolves smoothly according to the Schrödinger equation. The wave function spreads out. Superposition develops, everything is deterministic and predictable. But when you measure the system, something totally different happens. The wave function collapses instantaneously and randomly to one outcome. These two rules seem fundamentally incompatible. So, which one is right? Or more disturbingly, are they both right? And if so, what triggers the switch from one rule to the other? This is not an academic question. This is asking what reality is. Does superposition represent real physical states or just our ignorance? When a particle is in superposition, is it really in multiple states at once, or is it in one state that we just do not know? The experiments seem to clearly say that superposition is real. Interference patterns only make sense if the particle goes through both slits simultaneously. But if superposition is real, then where does it stop? When does a quantum system become classical? Think about Schrödinger's cat again. The radioactive atom that might decay is definitely quantum. It exists in a superposition of decayed and not decayed. But what about the Geiger counter that detects the decay? It is made of trillions of atoms. Is it quantum too? Does it enter a superposition of having detected the decay and not detected it? And what about the vial of poison that breaks when the Geiger counter triggers? Is that in superposition? And the cat's biological systems? Are they in superposition of functioning and not functioning? Where does the line get drawn? The Copenhagen interpretation, which was the dominant view for decades, says that macroscopic objects like cats and measuring devices are fundamentally classical. Quantum mechanics applies to microscopic systems, but somewhere in between microscopic and macroscopic there is a boundary. Above that boundary, things have definite states. Wave functions collapse when the quantum system interacts with a classical measuring device. This solves the measurement problem by just declaring that measurements are special. But this is deeply unsatisfying. Where is the boundary? What size qualifies as macroscopic? Is it 10 atoms, a million, a mole? And what makes measuring devices special? What exactly counts as a measurement? Some physicists, including some of the founders of quantum mechanics, thought that consciousness might be the key. Maybe wave functions collapse when a conscious observer becomes aware of the result. This would explain why measuring devices cause collapse, because eventually a human looks at the device. But this seems crazy. Are we really saying that the universe needs consciousness to function? That particles exist in superposition until a conscious being looks? What about before conscious beings evolved? Was the entire universe in superposition for billions of years? And what counts as conscious? Does a mouse collapse wave functions, a bacterium, an artificial intelligence? Most physicists today reject the consciousness interpretation. It seems too anthropocentric, too much like putting humans at the center of physics. But then, what does cause collapse? And more fundamentally, does collapse really happen at all? Maybe some physicists suggested we are asking the wrong question. Maybe the wave function never collapses. Maybe all the possibilities in the superposition are equally real, and measurement just tells us which branch of reality we find ourselves in. This is the many worlds interpretation, and we will explore its staggering implications later. But for now, the key point is this. The measurement problem reveals a gap in our understanding. Quantum mechanics is incredibly successful at predicting what happens in experiments, but it does not tell us what is real. It does not tell us what happens during measurement. It does not tell us where quantum behavior ends and classical behavior begins. And until we solve the measurement problem, we cannot confidently say whether the universe is quantum or classical or something in between. Except here is the thing. In the decades since the measurement problem was first recognized, physicists have made incredible progress understanding why we do not see quantum effects in big objects. And the answer is not that quantum mechanics stops working. The answer is that quantum effects become invisible when systems interact with their environment. The superposition does not disappear. It gets hidden. And this process, called decoherence, might be the key to understanding how a quantum universe produces our seemingly classical experience of reality. Chapter 9. Decoherence. Reality's stage trick. Imagine you are watching a magician on stage performing tricks. The magician makes a coin vanish. You know, the coin did not really vanish into thin air. It is still somewhere. The magician just hid it in a way that makes it impossible for you to see. Decoherence is nature's magic trick. It does not make quantum effects disappear. It makes them unobservable. And this might be the answer to why we do not see cats in superposition of alive and dead, even though the underlying quantum rules never stop applying. Let me explain how decoherence works. When a quantum system is isolated, completely cut off from its environment, it maintains its superposition beautifully. An electron in a laboratory vacuum chamber can remain in superposition for a long time. But nothing in the real world is perfectly isolated. Everything interacts with its environment. Air molecules bounce off it. Light photons scatter from it. It exchanges heat with its surroundings. And every one of these interactions causes decoherence. Here is what happens. Imagine that Schrödinger's cat is actually in a superposition of alive and dead. The alive cat is breathing, releasing molecules into the air, radiating heat, moving slightly. The dead cat is not doing these things. The environment around the cat, the air molecules and photons, becomes correlated with the state of the cat. The air molecules near the alive cat get pushed around differently than the air molecules near the dead cat. This means the environment becomes entangled with the cat. Now, here is the crucial point. Once the environment is entangled with the cat, you cannot see the quantum interference between alive and dead anymore. To see quantum interference, all parts of the superposition must be kept perfectly coherent. But now the environment is different for the alive branch versus the dead branch. The information about whether the cat is alive or dead has leaked into the environment. And since we cannot possibly keep track of all the trillions of air molecules and photons in the environment, we have lost the ability to observe the superposition. From our perspective, the cat appears to be either alive or dead, not both. This is a subtle point. The cat is still technically in superposition at the quantum level. But that superposition has become entangled with the environment in such a complex way that we can never see the quantum interference. The alive and dead branches have become effectively separate. They no longer interact. Each branch evolves independently. And we, as observers inside one branch, only see one outcome. From inside the system, it looks like the wave function has collapsed. But really, it has just decohered into branches that do not interfere with each other anymore. Decoherence happens incredibly fast for macroscopic objects. A dust grain floating in air decoheres in a tiny fraction of a second. A person decoheres essentially instantly because we are constantly interacting with our environment. We shed heat, we breathe, we reflect light. All these interactions spread information about our state into the environment. This is why you never find yourself in superposition of being in two different places. Not because you are not quantum, but because you decohere so fast that the superposition becomes unobservable before it can develop. But here is what is beautiful about decoherence. It explains why small systems can show quantum effects while big systems appear classical, without needing to postulate a fundamental boundary between quantum and classical. There is no boundary. Everything is quantum. Small systems just decohere slowly enough that we can see quantum effects before they disappear. Big systems decohere so fast that quantum effects become invisible immediately. The quantum mechanics never stops. It just gets obscured. And we can prove this. Scientists have demonstrated quantum effects in increasingly large systems by isolating them better and better from their environment. Superconducting circuits cooled to near absolute zero can maintain quantum superposition of electrical currents flowing in opposite directions around a loop. These are trillions of electrons all in superposition together, forming a current that goes both clockwise and counterclockwise simultaneously. We have put molecules containing over 2,000 atoms into superposition. We have created quantum states of mechanical oscillators that you could, in principle, see with a microscope. Every time we improve our isolation techniques, we can push quantum effects to larger scales. There's no sign of quantum mechanics breaking down. It is just decoherence hiding the quantum behavior. This has a profound implication. If decoherence explains why big things appear classical without quantum mechanics actually changing, then there is no reason to think quantum mechanics ever stops applying. The universe could be quantum at all scales, from particles to people to planets to the entire cosmos. Decoherence would explain why we see a definite, classical-looking world despite living in a quantum universe. The quantum superposition is still there, in the mathematics, in the wave function. We just cannot see it because we are entangled with our environment. Some physicists go further. They say decoherence solves the measurement problem. There is no collapse. There is just decoherence creating effectively separate branches of the wave function that no longer interfere. Each branch looks classical to observers inside that branch, but all branches remain real. This is the many worlds interpretation. And if it is right, then not only is the universe quantum, but there are infinitely many parallel quantum universes corresponding to every possible outcome of every quantum event. But before we go there, we need to see that quantum effects are not just theoretical abstractions. They exist in the real world at human scales. They exist in life itself. Chapter 10. Quantum Biology, Life's Secret. For a long time, biologists assumed that life was purely classical. Sure, life is made of atoms, and atoms are quantum. But living systems are warm, wet, and messy. They are the opposite of the cold, isolated environments needed to see quantum effects. Quantum mechanics, most biologists thought, was irrelevant to understanding life. They were wrong. In the past few decades, scientists have discovered that life does not just tolerate quantum effects. Life uses them. Quantum mechanics is not peripheral to biology, it is central. And this means that you, as a living being, are taking advantage of quantum weirdness right now inside your cells. Let us start with photosynthesis, the process plants use to turn sunlight into chemical energy. This is one of the most important processes on Earth. Nearly all life depends on it. When a photon of sunlight hits a leaf, it gets absorbed by a chlorophyll molecule. That energy needs to travel through a complex web of molecules to reach the reaction center, where it is converted to chemical energy. Classical physics says the energy should randomly walk through this web, bouncing from molecule to molecule, losing some energy at each step. But experiments show the energy reaches the reaction center with nearly perfect efficiency. Too good to be classical. In 2007, scientists discovered why. The energy exists in a quantum superposition of multiple paths simultaneously. Instead of taking one route through the molecular web, the energy takes all routes at once, trying every possible path in superposition. This allows the energy to find the most efficient route. If one path is blocked or inefficient, the other paths in the superposition compensate. It is like having 1,000,000 delivery drivers all trying different routes simultaneously, and then only the fastest one arrives. This is quantum coherence happening at room temperature inside a wet, chaotic leaf. Scientists were shocked. They did not think quantum coherence could survive in such a messy environment. But plants have been using this trick for billions of years. Then there are birds. Many birds can navigate using Earth's magnetic field, which is incredibly weak. How do they detect such a tiny field? The answer appears to be quantum entanglement. Inside birds' eyes, there are molecules called cryptochromes. When light hits a cryptochrome, it creates a pair of entangled electrons. The Earth's magnetic field affects the quantum state of these entangled electrons differently, depending on which direction the bird is facing. The bird's brain reads out this quantum information to determine direction. Birds are literally using entanglement to navigate. Every time a robin finds its way home, it is exploiting one of the strangest phenomena in quantum mechanics. Your sense of smell might also be quantum. The classical theory says smell works by the shape of molecules fitting into receptors in your nose, like a key fitting a lock. But this has problems. Sometimes molecules with very different shapes smell the same, while molecules with similar shapes smell different. An alternative theory, still controversial but gaining evidence, says that your nose detects the vibrational frequency of molecules using quantum tunneling. An electron in the receptor tunnels across a barrier only if the molecule vibrates at the right frequency to provide the energy needed. This would be quantum tunneling happening inside your nose every time you smell coffee. Enzymes, the molecular machines that catalyze chemical reactions in your body, appear to use quantum tunneling routinely. Classical chemistry says particles need enough energy to get over a barrier to react. Quantum tunneling says particles can go through the barrier instead, even without enough energy to go over. Enzymes seem to use tunneling to speed up reactions. Without quantum tunneling, many biological reactions would be too slow to sustain life. Your metabolism might depend on quantum effects. Some researchers even speculate that consciousness might involve quantum effects in the brain. This is highly controversial and not at all proven. But microtubules, structural proteins inside neurons, might be able to maintain quantum states. If quantum superposition and entanglement occur in the brain, they might play a role in how neurons process information. This is speculative, but it is not crazy. We know quantum effects occur in biology elsewhere, so why not in the brain? The point is not that we have proven all of biology is quantum. We have not. The point is that quantum effects are not limited to isolated laboratory conditions. Quantum superposition, entanglement and tunneling happen inside living organisms at body temperature in wet, noisy environments. Life found a way to harness quantum mechanics billions of years ago. If single-celled organisms can maintain and use quantum effects, if plants can exploit quantum coherence, if birds can use entanglement, then clearly quantum mechanics does not break down just because things are warm and complex. And you are made of the same stuff. Your cells use the same chemistry, the same types of molecules, the same basic processes. If quantum effects matter for photosynthesis and bird navigation and enzyme function, then quantum effects matter for you. You are not a classical object that happens to be made of quantum parts. You are a system where quantum effects play functional roles. You are a quantum thing. But we do not need to stop at biology. Humans have gone beyond just using quantum effects passively. We have learned to build machines that exploit quantum mechanics intentionally. And these machines are proving beyond any doubt that quantum effects can be controlled and utilized at human scales in room temperature environments. These machines are called quantum computers, and they might revolutionize technology while simultaneously proving that the universe really is quantum all the way up. Chapter 11. Quantum Computing, Harnessing the Weird. Let me tell you about one of the most astonishing technological achievements of the 21st century. In October 2019, Google announced that their quantum computer had achieved something called quantum supremacy. They had performed a calculation that would take a classical supercomputer 10,000 years in just 200 seconds. This was not incremental progress. This was a demonstration that quantum effects can be controlled and exploited at a scale large enough to do useful computation. And it proved something profound. Quantum mechanics does not break down when you scale it up. It still works, and we can use it. To understand why this matters, let me explain how quantum computers work. A normal computer stores information in bits. Each bit is either 0 or 1. A bit might be a tiny transistor that is either on or off. When your computer runs a program, It manipulates these bits according to logical rules. To solve a problem, a classical computer tries solutions one at a time. If there are 1,000,000 possible solutions, the computer might need to check all 1,000,000 before finding the right one. A quantum computer uses qubits instead of bits. A qubit is a quantum system that can be in a superposition of 0 and 1 simultaneously. Remember, superposition is real. The qubit is genuinely in both states at once. Now, here is where it gets powerful. If you have one qubit in superposition of 0 and 1, and you add a second qubit also in superposition, the system is now in a superposition of 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. All 4 states exist simultaneously. Add a third qubit, and you get a superposition of 8 states. Add a fourth qubit, and you get 16 states. The number of states in superposition doubles with every qubit you add. By the time you have 50 qubits, you have over 1 quadrillion states existing in superposition simultaneously. This means a quantum computer can, in a sense, try all those states at once. It is not that the computer is fast and checking them sequentially. The computer exists in a superposition where all possible answers are being processed simultaneously. For certain types of problems, this provides an exponential speed-up. Problems that would take classical computers longer than the age of the universe to solve become tractable on a quantum computer. But building a quantum computer is incredibly hard. Remember decoherence? Every time a qubit interacts with its environment, it decoheres. The superposition gets entangled with the environment and becomes unobservable. The quantum information is lost. This happens fast, in microseconds or milliseconds. To make quantum computers work, you need to isolate the qubits from their environment as much as possible. Google's quantum computer operates at temperatures colder than outer space, just a few thousandths of a degree above absolute zero. Even then, decoherence limits how long the qubits maintain coherence. Current quantum computers can only perform calculations that finish before decoherence destroys the quantum state. But here is the thing. It works. Despite the difficulties, despite decoherence, despite the challenge of controlling quantum systems, we have built machines that exploit superposition and entanglement to perform computations. IBM has quantum computers that people can access over the internet. Multiple companies and research labs are building increasingly powerful quantum processors. These are not theoretical devices. They are real machines made of superconducting circuits, trapped ions, or other quantum systems. And they prove that quantum effects can be maintained and controlled at scales large enough to do engineering with. Google's quantum supremacy achievement used 53 qubits. That is, 53 quantum systems, all in superposition and entanglement simultaneously. IBM recently unveiled a quantum processor with over 1,000 qubits. These are not individual atoms anymore. These are human-made structures, circuits that you could see with a microscope, all behaving quantum mechanically. We have scaled quantum mechanics from the atomic scale to the human scale. And quantum mechanics still works. The same rules that apply to electrons apply to these circuits. This is evidence that quantum mechanics does not have a built-in scale limit. As long as you can isolate the system from its environment well enough to prevent decoherence, quantum effects persist. There is no magical size where quantum mechanics says, "Sorry, I only work on small things." We have demonstrated quantum superposition in objects containing trillions of atoms. The limiting factor is not the size of the system. It is our ability to isolate it from decoherence. And quantum computing is not the only application. Quantum sensors can measure magnetic fields and de-gravitational waves with unprecedented sensitivity. Quantum cryptography allows for communication that is fundamentally impossible to eavesdrop on because measuring quantum states destroys them. Quantum metrology, quantum simulation, quantum communication networks, all of these technologies are being developed right now. They all rely on quantum mechanics working at scales large enough for humans to manipulate, and they all work. So when someone asks whether the universe is quantum, we can point to quantum computers and say, we have built quantum machines. We have made things behave quantum mechanically on purpose at scales we can engineer. If we can do it in a laboratory, if nature does it in biological systems, then what would prevent the rest of the universe from being quantum? The answer is nothing. There is no barrier. Quantum mechanics scales. And if quantum mechanics scales without limit, then the universe itself could be quantum. But to really answer this question, we need to look at the universe as a whole. We need to look at cosmology. We need to look at the Big Bang. Because if the universe started as something tiny, then it started as something quantum. And that changes everything. Chapter 12. Quantum Fields, the Real Reality. Everything I have told you so far about particles is, in a sense, a lie. Not a lie exactly, but a simplification. When physicists talk about electrons and photons and quarks as particles, they are using language that makes sense to us. We can imagine little balls bouncing around. But that is not what these things really are. The truth is far stranger and far more beautiful. At the deepest level, reality is not made of particles at all. Reality is made of fields, and these fields are quantum. This is not metaphorical. This is the most accurate description of reality that physics has achieved. And once you understand quantum field theory, you understand that the universe is fundamentally quantum, not just at small scales, but everywhere, always. So what is a field? A field is something that has a value at every point in space. Think about temperature in this room. Every location has a temperature. You could map it out. Near the heater, temperature is high. Near the window, maybe it is cooler. That map of temperature values is a temperature field. Or think about the wind. At every location, the wind has a speed and direction. That is a velocity field. Fields fill space. They are not objects in space. They are the space having properties. Now, quantum field theory says that reality is made of fields. There is an electron field that fills all of space. There is a photon field, a quark field. Each type of particle has a corresponding field. These fields are always there, everywhere. They permeate the entire universe. You are swimming in quantum fields right now. They are passing through your body. They are inside you, outside you, everywhere. So where do particles come from? Particles are excitations of these fields. They are ripples, waves, vibrations in the quantum fields. Imagine a perfectly still pond. That is the field in its ground state. Now throw a rock in the pond. A wave spreads out. That wave is like a particle. It is a localized disturbance in the field, but the wave is not separate from the water. The wave is the water, just in a particular pattern of motion. Similarly, an electron is not a separate thing flying through empty space. An electron is the electron field vibrating in a particular way. That vibration is what we call a particle. But remember, these are quantum fields. This means the fields obey quantum mechanics. The excitations of the fields can be in superposition. They can be entangled. They obey the uncertainty principle. When you see an electron behaving like a wave in the double-slit experiment, you are seeing the quantum nature of the electron field. The field is in superposition of different configurations, and we perceive that as a particle wave. This is the most important point. The fields are primary. The particles are secondary. The electron field is real and fundamental. Individual electrons are just patterns in that field, and the field exists everywhere. When you think there are no electrons near you, what you really mean is that the electron field near you is in its ground state, not excited. But the field is still there. Space is never empty. It is always filled with quantum fields. And here is where it gets truly weird. Because the fields are quantum, they have quantum fluctuations. Remember the uncertainty principle? It applies to fields too. A quantum field cannot be perfectly flat, perfectly at zero. It is always fluctuating, even in empty space. These fluctuations are called virtual particles. Pairs of particles and antiparticles pop into existence out of the quantum field, exist for a tiny moment, and then annihilate back into the field. This is happening everywhere, all the time. Right now, electron-positron pairs are spontaneously appearing and disappearing in the space between your eyes and this screen. They exist for such a short time that they cannot violate energy conservation thanks to the uncertainty principle. But they are real. We can measure their effects. One of the most famous predictions of quantum field theory is something called the Casimir effect. If you put two metal plates very close together in a vacuum, the quantum fluctuations of the electromagnetic field between the plates are restricted. Only certain wavelengths fit between the plates. But outside the plates, all wavelengths are possible. This creates an imbalance of quantum fluctuations that pushes the plates together. This is not a theory. This is measured. The vacuum of space is not empty. It is full of quantum fluctuations, and those fluctuations exert measurable forces. Space itself is alive with quantum activity. This means that what we call empty space, the vacuum, is actually an incredibly complex quantum system. The vacuum is the ground state of all the quantum fields, but that ground state is not nothing. It is a seething foam of quantum activity, virtual particles appearing and disappearing, quantum fields fluctuating. This is what space is. Not an empty stage for things to happen on, but a dynamic quantum entity in its own right. Now, think about what this means. If space is made of quantum fields, and those fields fill the entire universe, then the entire universe is a quantum system. There is no place you can go where quantum fields are not. There is no location that is outside quantum mechanics. From the smallest possible scale, the Planck scale, where space itself becomes quantum foam, all the way up to the larger scales we can observe, everything is quantum fields. Particles are patterns in those fields. Matter is excitations of those fields. Energy is disturbances in those fields. And you are a complex pattern of quantum field excitations that has organized itself in a way that can think and wonder about quantum fields. But we can go even deeper. If the universe is made of quantum fields, what about the universe itself? What about the Big Bang? What about the origin of space and time? If we look at the very beginning of the universe, we find that it was once so small, so compact, so dense, that it must have been a quantum object. And this is where cosmology and quantum mechanics collide in the most spectacular way. Because if the universe started quantum and it is made of quantum fields, then the universe has been quantum from the very beginning. And all the structures we see, galaxies and stars and planets and people, might have come from quantum fluctuations at the birth of the cosmos. Chapter 13. Quantum Cosmology. The Birth Mystery. Let me take you back to the beginning. Not the beginning of your life or the beginning of human history, but the beginning of everything. 13.8 billion years ago, the universe was born in an event we call the Big Bang. But calling it an explosion is misleading. It was not an explosion into space. It was an explosion of space. Space itself came into existence and has been expanding ever since. Time itself began at the Big Bang. Before the Big Bang, the words before and time do not even make sense. This is already mind-bending, but it gets stranger. Because if we trace the universe back to its earliest moments, it becomes clear that the entire universe was once quantum. Here is why. The universe today is huge, about 93 billion light-years across in the part we can see. But if we run the expansion backward, rewinding cosmic history, the universe gets smaller and smaller. 1 billion years ago, everything was closer together. 10 billion years ago, even closer. Go back to the moment of the Big Bang, and all the space in the entire observable universe was compressed into a region smaller than an atom, smaller than a proton, smaller than anything we can even measure. At that size, quantum mechanics is not optional. It is mandatory. The universe was a quantum object. Think about what this means. Every rule we have learned about quantum mechanics, superposition, uncertainty, entanglement, applied to the entire universe at its birth. The universe itself was in a quantum state. But what does that even mean? What is the quantum state of a universe? This is where physics gets truly speculative, but also truly exciting. Cosmologists have developed something called quantum cosmology, the application of quantum mechanics to the universe as a whole. And it leads to some astonishing ideas. One of the most successful theories in cosmology is called inflation. In the first tiny fraction of a second after the Big Bang, the universe expanded exponentially fast. In less than a trillionth of a second, the universe grew from subatomic size to macroscopic size. This sounds insane, but inflation solves many problems in cosmology and makes predictions that have been confirmed by observations. But here is the key point. During inflation, the universe was so small that it was quantum, and quantum fields were fluctuating due to the uncertainty principle. These quantum fluctuations got stretched by inflation. Tiny quantum ripples in the fabric of space got blown up to cosmic sizes. After inflation ended, these ripples became tiny variations in the density of matter. Regions that were slightly denser than average had a bit more gravitational pull. Over millions and billions of years, those denser regions attracted more matter. They grew into galaxies. The quantum fluctuations became the seeds of all cosmic structure. Every galaxy, every star, every planet, every atom in your body can trace its origin back to quantum fluctuations in the first fraction of a second after the Big Bang. This is not speculation. We can see these quantum fluctuations. The cosmic microwave background radiation, the afterglow of the Big Bang, has tiny temperature variations across the sky. These variations match exactly what we would expect from quantum fluctuations stretched by inflation. The predictions of quantum cosmology match observations to extraordinary precision. The universe shows us its quantum baby picture, and we can see the fingerprints of quantum uncertainty written across the sky. Let me say that again, because it is so important. The galaxies exist because of quantum randomness. The uncertainty principle caused fluctuations in quantum fields during inflation. Those fluctuations became density variations. Those density variations became galaxies. If quantum mechanics did not exist, if the uncertainty principle did not cause fluctuations, the universe would be perfectly uniform. No galaxies, no stars, no planets, no life. We exist because the universe is quantum. But there is something even deeper here. At the moment of the Big Bang itself, the universe was so small that not just matter, but space and time themselves must have been quantum. What does it mean for space to be quantum? What does it mean for time to be quantum? These are questions that physicists do not fully know how to answer yet. We do not have a complete theory of quantum gravity, a theory that combines quantum mechanics with general relativity to describe space-time as a quantum entity. But we know such a theory must exist, and we know it will tell us that at the Planck scale, about 10 to the minus 35 meters, space-time itself becomes a quantum foam, a bubbling froth of quantum fluctuations where the very notions of space and time break down. Some physicists have proposed that the universe itself emerged from a quantum fluctuation. Perhaps in a strange quantum sense, the universe tunneled into existence out of nothing. Or perhaps time is cyclic and quantum in a way we do not yet understand. These ideas are at the frontier of physics, and we do not know which, if any, are correct. But they all share one thing. They treat the universe as a quantum system from the very beginning. And if the universe started quantum, and it has been expanding and evolving according to the laws of quantum field theory ever since, then the universe has always been quantum. There was never a moment when the universe transitioned from quantum to classical. Classical behavior is just what quantum systems look like when they're big and decohered. But underneath, the quantum nature remains. The universe today is the evolved quantum state of the tiny quantum universe at the Big Bang. The wave function of the universe has been evolving for 13.8 billion years. And we are part of that wave function. We are excitations of quantum fields that have arranged themselves into complex patterns capable of asking questions about quantum fields. This brings us to perhaps the most radical interpretation of quantum mechanics, an interpretation that takes the quantum nature of the universe to its logical extreme. An interpretation that says there is not just one universe, but infinitely many. An interpretation that says every possible outcome of every quantum event actually happens in some parallel reality. This interpretation is called many worlds, and if it is correct, then the quantum universe is even stranger and vaster than we imagined. Chapter 14. Many Worlds, the Ultimate Possibility. Let me tell you about an idea so radical, so mind-bending, so seemingly crazy that many physicists dismissed it when it was first proposed in 1957. But this idea solves the measurement problem completely. It explains why we see definite outcomes when quantum mechanics predicts superposition. It removes the need for wave function collapse entirely. And an increasing number of physicists think it might actually be true. The idea is called the many worlds interpretation, and it says that every time a quantum measurement happens, the universe splits into multiple copies, one for each possible outcome. Every possibility in the quantum superposition actually occurs in a separate branch of reality. And this splitting happens constantly, trillions of times per second, creating an unimaginably vast multiverse of parallel universes. Let me explain how this works. Remember the measurement problem? Quantum mechanics says systems evolve in superposition until measured. Then the wave function collapses to one outcome. But the theory does not explain what causes collapse or what counts as a measurement. Hugh Everett, a graduate student in physics, asked a simple question. What if there is no collapse? What if the wave function always evolves according to the Schrödinger equation, and all outcomes in the superposition actually happen? Here is how it would work. An electron approaches the double slits in superposition of going through the left slit and the right slit. In the standard interpretation, when we measure which slit, the wave function collapses and we see one outcome. In the many worlds interpretation, there is no collapse. The wave function continues to evolve in superposition. But the observer also becomes entangled with the electron. If the electron goes through the left slit, the observer sees left. If the electron goes through the right slit, the observer sees right. So the combined system of electron plus observer enters a superposition of two states. Electron, left, plus observer sees left, and electron, right, plus observer sees right. Both outcomes are real. Both actually happen. but they happen in separate branches of the wave function that no longer interact with each other. From inside one branch, the observer only sees one outcome, so it looks like collapse happened. But from a view outside the system, both branches exist. The observer has split into two copies, one in each branch, each seeing a different outcome. And because the branches do not interact anymore due to decoherence, neither copy of the observer knows the other exists. This is wild. It says that every time you make a quantum measurement, you split into multiple copies. Right now, as quantum events happen in your brain and body, you are constantly splitting. There are versions of you in other branches of the wave function experiencing different outcomes of quantum events. Most of these differences are tiny, happening at the atomic level. But occasionally, quantum events have macroscopic consequences. In some branch, you took a different route to work today. In some branch, you are pursuing a different career. In some branch, the cosmic ray that almost caused a mutation in your grandmother's DNA actually did cause that mutation, and you were never born. The many worlds interpretation says all possible histories actually happen. Every time a quantum event could go multiple ways, it does go multiple ways in different branches. The wave function of the universe is a superposition of all these branches, constantly splitting as quantum events unfold. The number of branches is enormous, perhaps infinite, and growing exponentially with every moment. But we only experience one branch, our own timeline, because decoherence prevents the branches from interfering with each other. Now, you might ask, where does the energy come from to create all these extra universes? This is a common objection, but it misunderstands what is happening. The total wave function does not gain energy, it just evolves into a superposition of branches. Each branch has the same energy as the original system. It is not that new universes are being created with new energy. It is that the one universe, described by one wave function, is becoming more and more complex, with more and more branches. From inside, it looks like separate universes. From outside, it is one quantum state evolving. Is this true? We do not know. Many worlds is an interpretation of quantum mechanics, not a separate theory. It makes the same predictions as other interpretations for any experiment we can actually perform. So we cannot test it directly. But it has advantages. It is mathematically simpler than other interpretations because it does not require adding wave function collapse as a separate rule. It is deterministic. The wave function evolves smoothly according to one equation. And it takes quantum mechanics seriously, applying it to everything including observers, without introducing arbitrary boundaries between quantum and classical. Many worlds is controversial. Some physicists love it, some hate it, some think it is obviously true, some think it is nonsense. But here is the thing. Many worlds takes the quantum nature of the universe to its ultimate conclusion. If quantum mechanics applies to everything, including observers and measuring devices and the whole universe, then superposition never ends. All possibilities remain real, just in different branches. The universe, in this view, is a vast quantum superposition of every possible history. Every quantum fluctuation creates new branches. and every one of those branches is as real as ours. Whether or not many worlds is correct, it represents the logical endpoint of taking quantum mechanics seriously at all scales. It says the universe is not just quantum at small scales. The universe is quantum, period. And that quantum nature has the most profound implications imaginable. We do not just live in a quantum universe. We live in a quantum multiverse of all possible quantum universes. Reality is not one definite sequence of events. Reality is a superposition of all possible sequences, and we are quantum beings experiencing one branch of that infinite superposition. But there is still one piece of the puzzle missing. We have talked about quantum mechanics applying to matter and energy. We have talked about it applying to the early universe. But there is one force that does not fit. One part of physics that stubbornly resists being made quantum. And until we solve this problem, we cannot say with complete confidence that everything is quantum. We need to talk about gravity. Chapter 15. Quantum gravity. The missing piece, gravity, is the odd one out. We have quantum field theories for 3 of the 4 fundamental forces. Electromagnetism is described by quantum electrodynamics. The strong nuclear force is described by quantum chromodynamics. The weak nuclear force is part of the electroweak theory. All 3 are quantum field theories. They work spectacularly well. But gravity, described by Einstein's general relativity, is classical. It is a theory of smooth, continuous space-time geometry, and nobody knows how to make it quantum. This is not for lack of trying. Physicists have been attempting to create a quantum theory of gravity for almost a century. The problem is that gravity is fundamentally different from the other forces. In quantum field theory, forces are exchanges of particles. Electromagnetism is mediated by photons. The strong force is mediated by gluons. These are excitations of quantum fields happening within space-time. But gravity is space-time. In general relativity, mass and energy curve space-time, and that curvature is gravity. Objects follow curved paths, not because a force pushes them, but because space-time itself is curved. So quantizing gravity means quantizing space-time itself. It means treating space and time as quantum fields. And that is much harder. Why do we need quantum gravity? For most practical purposes, we do not. Classical general relativity works perfectly for planets and stars and even black holes, as long as we stay outside the event horizon. But there are situations where both quantum mechanics and gravity are important simultaneously. The centers of black holes, where matter is crushed to infinite density. The moment of the Big Bang, when the universe was Planck scale. These are regimes where we need a quantum theory of gravity to describe what happens, and our current theories simply break down there. They give nonsensical answers like infinities and singularities. One of the biggest clues that gravity must be quantum comes from black holes. In the 1970s, Stephen Hawking combined quantum field theory with general relativity and discovered something shocking. Black holes are not perfectly black. Quantum effects near the event horizon cause black holes to emit radiation. This Hawking radiation means black holes slowly evaporate over time. A black hole is a quantum object, even though we describe it with classical general relativity. But Hawking radiation creates a paradox. When a black hole forms and then evaporates, what happens to the information about what fell in? In quantum mechanics, information cannot be destroyed. The wave function always evolves reversibly. But if a black hole swallows information and then evaporates, the information seems to disappear. This is the black hole information paradox. Solving it requires understanding quantum gravity. We need to know what really happens at the center of a black hole, where both quantum effects and gravitational effects are strong. So, what are the candidates for a quantum theory of gravity? The most famous is string theory. Instead of particles being point-like, string theory says they are tiny, vibrating strings. Different vibrations of the string correspond to different particles. One vibration is an electron, another is a photon. And crucially, one vibration is a graviton, the hypothetical quantum particle that mediates gravity. String theory naturally includes gravity as a quantum force. It also requires extra dimensions of space beyond the three we experience. These extra dimensions are curled up so small we cannot see them. String theory is mathematically beautiful and has inspired enormous amounts of research, but it has a problem. It makes almost no testable predictions at accessible energies. We cannot build experiments that probe the energy scales where string theory becomes important. Another approach is loop quantum gravity. Instead of replacing particles with strings, loop quantum gravity keeps particles as particles but quantizes space-time itself. Space becomes discrete, made of tiny loops braided together. These loops are so small that space appears continuous at everyday scales, but at the Planck scale, space has a granular structure. Loop quantum gravity suggests that the Big Bang was not a singularity, but a big bounce, where a previous contracting universe rebounded into our expanding universe. Loop quantum gravity also has problems, including difficulty connecting to the standard model of particle physics. There are other approaches too. Causal sets, where space-time is made of discrete points with causal relationships. Asymptotic safety, where gravity becomes quantum at high energies in a particular mathematical way. Emergent gravity theories, where space-time and gravity are not fundamental but emerge from something deeper, perhaps quantum entanglement itself. All these theories are incomplete. All have unsolved problems. None have been confirmed by experiment. We do not yet have a confirmed theory of quantum gravity. But here is what almost everyone agrees on. Gravity must become quantum at some scale. We know this because the universe was once Planck scale, and at that size, quantum effects dominate everything. We know this because black holes exhibit quantum behavior. We know this because all other forces are quantum, and it would be bizarre for one force to be fundamentally different. When we finally figure out quantum gravity, it will almost certainly tell us that space-time itself is quantized. Space and time will turn out to be made of discrete quantum units, quantum foam at the smallest scales. Space and time will not be smooth continua, but quantum fields like everything else. And if space-time is quantum, then literally everything is quantum. Matter is excitations of quantum fields. Energy is excitations of quantum fields. Forces are interactions of quantum fields, and now space and time themselves are quantum. There is nothing left that is not quantum. The universe, at its deepest level, is quantum through and through. From the tiniest possible scale to the largest cosmic scales, from the moment of the Big Bang to the present day, from particles to people to planets to the fabric of space-time itself, everything is quantum. The universe is not partially quantum. It is not quantum with some classical exceptions. It is quantum. Period. We have followed the evidence from particles to cells to computers to the cosmos. We have seen quantum effects in laboratory experiments, in living organisms, in technological applications, in the structure of the early universe. Every time we look for quantum behavior, we find it. Every time we try to scale it up, it still works. There is no boundary where quantum mechanics stops. There is no size limit, no complexity limit, no temperature limit where quantum rules suddenly change into something else. There is just decoherence, hiding quantum effects from our view while they continue underneath. So now we can finally answer the question we started with. Is this whole universe a quantum thing? The evidence is overwhelming. The answer is yes. Chapter 16. Adding up the evidence. Let us take stock of everything we have learned on this journey. We started with the simple question about whether the universe is quantum. We have travelled from the double-slit experiment to quantum fields, from Schrödinger's cat to the Big Bang, from particles to parallel universes. And everywhere we looked, we found the same answer. Quantum mechanics is not a theory about small things. It is a theory about everything. Let me summarize the case. First, we learned that quantum mechanics is real. It is not a mathematical trick or a convenient fiction. Superposition is real. Entanglement is real. Uncertainty is real. These are features of reality itself, confirmed by countless experiments over 100 years. Every single test of quantum mechanics has confirmed its predictions. No experiment has ever shown quantum mechanics to be wrong. It is the most accurately tested theory in the history of science, with predictions verified to 10 decimal places. Second, we learned that quantum mechanics applies to increasingly large systems. We started with electrons and photons, particles we cannot see. But then we found quantum effects in atoms, molecules, superconducting circuits, mechanical oscillators. Every time someone said quantum effects would disappear at some scale, experiments proved them wrong. We have demonstrated quantum superposition in molecules with thousands of atoms. We have built quantum computers with thousands of qubits. The limit is not size. The limit is decoherence. As long as we can isolate a system from its environment, quantum effects persist regardless of size. Third, we learned that life uses quantum mechanics. Photosynthesis uses superposition. Bird navigation uses entanglement. Enzymes use tunneling. Quantum effects are not too delicate for biology. Life has been exploiting quantum mechanics for billions of years. You are a biological organism. Your cells use the same quantum chemistry that all life uses. You are not a classical machine that happens to be made of quantum parts. Quantum effects play functional roles in your biology. Fourth, we learned that the universe started quantum. At the Big Bang, everything was compressed to subatomic size. At that scale, quantum mechanics is mandatory. The quantum fluctuations during inflation became the seeds of all cosmic structure. Galaxies exist because of quantum uncertainty. The cosmic microwave background shows us the quantum fluctuations from the early universe. We can literally see the quantum nature of the universe written across the sky. The universe did not transition from quantum to classical. It started quantum and has remained quantum. Fifth, we learned that quantum fields are fundamental. Reality is not made of particles in space. Reality is made of quantum fields filling all of space. Particles are excitations of those fields. Space itself is never empty. It is always full of quantum fields undergoing quantum fluctuations. Virtual particles pop in and out of existence everywhere. The vacuum is not nothing. It is a quantum system. And these quantum fields extend throughout the entire universe. There is no location that is outside quantum field theory. Sixth, we learned that gravity must be quantum too. We do not yet have a complete theory of quantum gravity, but we know space-time itself must become quantum at small enough scales. Black holes emit quantum radiation. The Planck scale must be quantum foam. When we finally solve quantum gravity, it will tell us that space and time are quantized. And then there will be nothing left in physics that is not quantum. Now, let me address the obvious question. If everything is quantum, why does the world look classical? Why do we not see ourselves in superposition? The answer is decoherence. When a quantum system interacts with its environment, the superposition becomes entangled with the environment in a way that makes the quantum interference invisible. The system appears to be in one definite state, but really it is still in superposition, just spread across environmental degrees of freedom we cannot track. Decoherence happens incredibly fast for large objects like people. We decohere instantly because we're constantly interacting with light, air and thermal radiation, so we never see ourselves in superposition. But that does not mean we are not quantum. It means we are quantum systems that decohere too fast to observe our own superposition. The many worlds interpretation takes this to its logical conclusion. It says we are in superposition, constantly. Every version of every possible outcome exists in some branch of the wave function. We just do not notice because decoherence separates the branches. Each version of you experiences one branch and thinks that is the only reality. But all branches are equally real. The universe is one giant quantum superposition, and we are parts of that superposition experiencing one slice of it. Whether you accept many worlds or not, the basic point remains. There is no evidence for a fundamental boundary between quantum and classical. Classical behavior emerges from quantum mechanics through decoherence. It is not a separate kind of physics. It is what quantum mechanics looks like when systems are large and coupled to their environment. Underneath the classical appearance, the quantum nature remains. The universe never stops being quantum. We just stop being able to see it. So is the universe quantum? Look at the evidence. Quantum mechanics applies to everything ever tested. It applies to particles, atoms, molecules, materials, biological systems, technological systems. It describes the early universe and the cosmic microwave background. It will eventually describe gravity and space-time. It is unlimited by scale, complexity, or domain. And there is no competing theory. There is no alternative framework that explains all these phenomena without quantum mechanics. Classical physics fails to explain the double-slit experiment. It fails to explain atomic spectra. It fails to explain chemistry and the periodic table. It fails to explain how stars shine. It fails to explain superconductivity and superfluidity and countless other phenomena. Only quantum mechanics explains all of this. The most honest answer, based on all available evidence, is yes. The universe is quantum. Not just some parts of it, not just at small scales. The universe is fundamentally, comprehensively, completely quantum, and that includes you. Chapter 17. What this means for you. So what does it mean to live in a quantum universe? What does it mean for you to be a quantum thing? Let me bring this full circle and make it personal. Because this is not just abstract physics. This is about the nature of your existence, about what you really are, about how you relate to the cosmos. You are made of atoms. About 7 billion atoms. That is a 7 followed by 27 zeros. Every single one of those atoms is a quantum object. The electrons in those atoms exist in quantum orbitals, probability clouds around the nucleus. They do not have definite positions. They are spread out in superposition of many locations simultaneously. The chemical bonds that hold your molecules together are quantum mechanical. The electron sharing that creates bonds depends on quantum superposition and the Pauli exclusion principle. Without quantum mechanics, atoms would not form molecules. Chemistry would not work. You could not exist. Every breath you take involves quantum mechanics. The oxygen molecules you inhale interact with hemoglobin in your blood through quantum chemical bonds. The electrons in the hemoglobin enter a different quantum state when oxygen binds, changing the properties of the molecule. This is quantum mechanics in action inside your body right now. Every process in your cells, every enzyme reaction, every signal transmitted between neurons, everything is governed by quantum rules. You are not a clockwork machine made of billiard balls. You are a pattern of quantum fields arranged in a specific configuration. The atoms in your body were not always part of you. Carbon atoms in your body were forged in the cores of massive stars billions of years ago. Those stars underwent fusion, a quantum tunneling process, where atomic nuclei combined through quantum probability. When those stars exploded as supernovae, they scattered those atoms into space. Eventually, those atoms became part of the molecular cloud that collapsed to form the solar system. They became part of Earth. They were cycled through rocks, atmosphere, oceans, and living organisms for billions of years before becoming part of you. Every atom has a quantum history stretching back to the Big Bang, and those atoms will not always be part of you. You are constantly exchanging atoms with your environment. Every breath, every meal, every shed skin cell. The atoms that are you today will disperse back into the environment when you die. They will become part of soil, plants, animals, other people. You are a temporary pattern in the flow of quantum matter through the universe. The pattern changes continuously while maintaining the identity we call you. What makes you you is not the specific atoms, but the pattern, the information, the quantum state. And that pattern is quantum through and through. Now think about consciousness, about your subjective experience of being you. We do not fully understand how consciousness arises from physical processes. This is one of the deepest mysteries in science and philosophy. But whatever consciousness is, it emerges from the quantum processes in your brain. Your neurons are quantum systems. The synapses between neurons involve quantum chemistry. If quantum effects play any role in neural processing, and they almost certainly do at the molecular level, then your thoughts and feelings have a quantum component. When you make a decision, quantum events in your brain might play a role. If many worlds is correct, there are versions of you in other branches who made different decisions at quantum branch points. Every version is you, experiencing a different quantum outcome. This might sound disturbing. If quantum events are random, does that mean you do not have free will? If your decisions have a quantum random component, are you not in control? These are deep questions. But consider this. Maybe freedom is randomness. Classical determinism means the future is completely determined by the past. You could not have done otherwise. Quantum mechanics introduces genuine randomness into the universe. Your future is not predetermined. Multiple futures are possible. Which one occurs depends on quantum events. Perhaps that randomness is what allows for genuine choice, genuine freedom, genuine creativity. Perhaps a quantum universe is the only kind of universe where freedom is possible. Or, if you prefer, the many worlds view. Every possible version of you makes every possible choice in different branches. All your potential selves exist. Every road not taken is taken in some branch. This is either terrifying or liberating, depending on how you look at it. It means that in some sense you are not limited to one life, one history, one set of experiences. In the vast quantum multiverse, every version of you exists. Every possibility is realized somewhere. But regardless of interpretation, the basic fact remains. You are quantum. Not metaphorically, not approximately. You are a localized excitation of quantum fields, a pattern of wave functions that has organized itself into a structure capable of self-awareness. You emerged from quantum fluctuations in the early universe. You are made of atoms forged in quantum processes in stars. You are sustained by quantum chemistry in your cells. Your very existence is a testament to the quantum nature of the universe, and you are not separate from the universe. There is no clear boundary where you end and the environment begins. You are constantly exchanging atoms, energy, and information with your surroundings. At the quantum level, you are entangled with the environment. The universe does not contain you. You are part of the universe. You are the universe experiencing itself, a portion of the cosmic quantum wave function that has become conscious and is looking back at the rest of itself in wonder. So when you look at that coffee cup from the very beginning of this video, you are not separate from it. You are both quantum systems, both patterns of quantum fields, both parts of the universal wave function. The cup is made of the same kinds of atoms as you. Those atoms obey the same quantum rules. The only difference is the pattern, the arrangement, the specific quantum state. And that state is constantly changing, evolving, interacting. The cup is not a separate, isolated object. It is connected to everything else through quantum fields that fill all space. And so are you. To live in a quantum universe is to live in a universe that is fundamentally interconnected. Everything is made of the same quantum fields. Everything obeys the same quantum rules. Everything was born from the same quantum fluctuations in the early universe. You are not an isolated fragment of matter in an empty void. You are an integral part of a unified quantum whole. Your atoms are recycled stardust. Your consciousness emerges from quantum processes. Your fate is linked to the quantum evolution of the cosmos. You are a quantum being in a quantum universe. And that is both humbling and beautiful. The universe is not a clockwork machine. It is not deterministic and predictable. It is not separate objects following fixed trajectories. The universe is a vast superposition of possibilities, a quantum wave function evolving according to the Schrödinger equation, constantly branching into new configurations. It is uncertain, probabilistic, interconnected, strange beyond our everyday intuition. But it is also more real, more rich, more astonishing than the classical universe we once thought we lived in. The quantum universe is alive with possibility. It is creative, it is surprising, it contains depths we are still exploring and mysteries we have not solved. And you are part of that mystery. You are one of the ways the quantum universe has organized itself to become aware of its own quantum nature. You are how the universe studies itself. You are a quantum thing asking whether the universe is a quantum thing. And the answer, beautifully, is yes. We have reached the end of our journey. We asked a simple question. Is this whole universe a quantum thing? And we have arrived at an answer, yes. Overwhelmingly, conclusively, beautifully yes. The universe is quantum. From the smallest particles to the largest galaxies, from the moment of creation to the present day, from the fundamental fields that constitute reality to the patterns of thought in your mind, everything is quantum. This is not speculation. This is the result of 100 years of experimental verification, of theoretical development, of technological application. Quantum mechanics is not a hypothesis. It is a tested, confirmed, established description of how reality works. But answering this question has opened up bigger mysteries. We know the universe is quantum, but we do not know why these particular quantum rules. Why does nature allow superposition? Why is there an uncertainty principle? Why do measurements cause apparent collapse? Why does the universe have quantum fields rather than being made of something else entirely? These are deep questions that physics cannot yet answer. We have discovered how the universe works at the quantum level. We have not discovered why it works this way. Perhaps there is no deeper why. Perhaps quantum mechanics is simply the fundamental level of reality, and asking why is like asking what is north of the North Pole. Or perhaps there is another layer beneath, some more fundamental theory from which quantum mechanics emerges. Nobody knows, and we do not have all the answers even within quantum mechanics. We do not have a complete theory of quantum gravity. We do not know whether wave function collapse is real or whether many worlds is correct. We do not fully understand how consciousness relates to quantum mechanics. We do not know if there are limits to superposition that we have not yet discovered. Physics is not finished. The quantum universe still holds secrets, but that is what makes it exciting. Science is not about reaching final answers and being done. Science is about asking better questions, making better observations, building better theories. Every answer leads to new mysteries. Every solution opens new problems. And that is wonderful. The quantum universe is far stranger than the classical universe people believed in 100 years ago. It is stranger than most people imagine even today. But strange does not mean incomprehensible. We can understand quantum mechanics, at least mathematically. We can make predictions. We can build technology that exploits quantum effects. We can trace our own origins back to quantum fluctuations at the dawn of time. We can recognize ourselves as quantum beings in a quantum cosmos. The universe has revealed its quantum nature to us, and that revelation is one of the greatest achievements of human thought. Think about what this means for humanity. For nearly all of history, humans did not know what things were made of. We did not know about atoms, let alone quantum mechanics. In just over a century, we have progressed from discovering the electron to building quantum computers and understanding the quantum origin of galaxies. This is astonishing, and we are just getting started. Quantum technologies are in their infancy. Quantum biology is a young field. Quantum cosmology still has fundamental questions to answer. The 21st century will be the century when humanity fully embraces its quantum nature and learns to work with quantum mechanics at all scales. So look around you. Look at the room you are in, the screen you are watching, the device playing this video, your own hands. Everything you see is quantum. The light entering your eyes is made of photons, quantum particles. The atoms in your retina absorb those photons through quantum transitions. The signals sent to your brain involve quantum chemistry. The very act of perception is quantum. You are not looking at a classical world from outside. You are a quantum system interacting with other quantum systems, all part of the universal quantum wave function. There is no separation. There is only participation. And when you look up at the night sky, you are looking at a quantum universe. The stars are fusion reactors powered by quantum tunneling. The light from those stars travels as photons, quantum particles that are also waves. That light has been traveling for years, decades, centuries, carrying information about the quantum processes in distant stars. The galaxies you see formed from quantum fluctuations in the early universe. The very space between the stars is filled with quantum fields undergoing quantum fluctuations. Everything is quantum. Everything has always been quantum, and everything will remain quantum forever. This is your heritage as a conscious being in this universe. You are made of stardust, and that stardust is made of quantum fields. You emerge from quantum chaos at the Big Bang. You are sustained by quantum processes in your cells. You are connected to everything else through the quantum fabric of reality. You are a node in the vast network of quantum entanglement that links all things. You are a pattern in the cosmic quantum wave function. You are the universe become conscious of itself. And the universe you have become conscious of is quantum through and through, in every way, at every scale, with no exceptions. The coffee cup from the beginning is not just a ceramic object holding liquid. It is a quantum marvel, a complex arrangement of atoms existing in probability clouds, held together by quantum bonds, made of matter forged in quantum fusion in ancient stars, shaped by quantum processes in a ceramic kiln. And when you hold that cup and feel its warmth and taste its contents, you are a quantum being interacting with another quantum structure through quantum fields that extend throughout all reality. The cup is not separate from you. You are both waves in the quantum ocean of existence. You are both notes in the grand quantum symphony of the cosmos. You are both quantum things in a quantum universe. And now you know. You know what you are made of. You know how you relate to the universe. You know that the reality you experience is just the surface of a deeper quantum reality. You know that the strange, wonderful, bizarre rules of quantum mechanics are not distant abstractions, but the very rules that govern your existence. You are quantum. The universe is quantum. And that is one of the most profound truths that science has ever discovered. Thank you for joining me on this journey from particles to the cosmos, from the double-slit experiment to the quantum fields that fill all reality. Thank you for thinking deeply about these strange ideas. Thank you for being curious about the nature of existence. The universe is quantum, and so are you. Never forget that. Every time you look at anything, remember, you are looking at quantum fields. Every time you think a thought, remember, quantum processes made that thought possible. Every time you wonder about your place in the cosmos, remember, you are the cosmos, a localized piece of the universal quantum wave function, the universe experiencing itself from one particular quantum state. That is what you are. That is what everything is. Quantum. Always quantum. Forever quantum. The universe is a quantum thing, and so it has always been, and so it will always be. And that is beautiful.